lesson, we're going to continue our learning in numbers theory. Um, and Today, this part, we're going to review a very interesting topic about primes or prime numbers. This is actually, um, there was a lot of researches in the past 100 years. People are trying to looking for all different properties or conclusions that can be derived from prime numbers, and it actually quite useful and being applied in many different areas today, such as encryption, decryption, um, things like that. And in this lesson, we're going to start with the basic definition of prime numbers, and then we'll learn the prime factorizations, and eventually we'll take a look at the fundamental theory of arithmetic. So let's start with the definition of prime numbers. So what are prime numbers? So what are these numbers when people talking about primes? So from the previous classes, we see many different numbers. Some numbers are divisible by other numbers, like for example 9 is divisible by 3. I have 8 is divisible by 4, but there are also some numbers that are not divisible by many other numbers, like for example 7 cannot be divisible by 2, not divisible by 3, not divisible by 4, not divisible by 5, not divisible by 6. So looks like this number, of course every number is divisible by 1, it is yourself, and this number can also be divisible by 7, which is itself, and the result is always 1. So which means no matter how odd this number it is, another example which is 11, you looks like not divisible by many different numbers, but at least you always divisible by 1, and you always divisible by yourself. So we call this type of numbers prime numbers. In other words, other than the number of 1 and the number of itself, it has no other factors within it. The prime number here we still narrow it down within positive number only. So the prime number is a positive integer, because negative number is really just a mirror of the positive side. So it's a positive integer that is divisible by exactly 2 numbers. Exactly 2 positive integers. That is 1 and the number itself. And correspondingly, we have prime numbers. So how do we call other numbers if they do have different factors? We call them composite number. So a composite number is a positive integer that is divisible by more than two positive integers. Right, so this is it's an opposite conclusion from prime number. Prime number can only be divisible by exactly two positive integers, which are the number one number itself, because any number can be divisible by one and by itself. But composite number means you can have further factors, you can be further divisible by other integers, so you have more than two positive integers that are divisible. Like for example, the number of 8 is of course divisible by 1 and by itself, but it can also be divisible by 2 and by 4. So at least it has more than two factors. So which means number 8 is not a prime number, it is a composite number. So now let's list all the numbers within 20 to see how many of them are primes and how many of them are not prime. Later on, you have a reference table where you can be easily find such information from online, that people can listing all the prime numbers up to a very large number. For example, you can easily find all the prime numbers within 100, you can easily find all the prime numbers within 10,000 or within 100,000 or even within 1 million. So basically people are able to listing a lot many known prime numbers. But as a practice, if we start looking at the first 20 integers, what are the prime numbers from there? So first of all, number 1 is not a prime. This is because 1 is only divisible by 1 and itself is also 1. So it's not exactly two positive divisors, it's actually only have one positive factor. So based on the definition of the fact is that the number 1 is actually not a prime number. Then how about 2? So number 2 is a prime number because it cannot further decompose it with other factors. It can only be divisible by 1 and by itself, which is 2. So 3 is also prime, and 4 is not, right? Because besides 1 and itself, number 4 is also divisible by 2, so it's not a prime. So similarly, actually here I can stop here and then cross out all the even numbers. Remember the conclusion we had from last class, there's a easier way to determine whether a number is divisible by 2, and our conclusion is that all the even numbers are divisible by 2. So for any even number that other than 2 itself, they are divisible by 2, which means they have at least one more factor other than 1 and itself that is a factor of this number, so that they do not satisfy the definition of prime number because they have more than exactly 2 positive factors. So this is actually not only applies to the numbers within 20, but it applies to all positive integers. So other than 2, all other even numbers are not a prime number. Then we go back to here, keep checking the rest of the odd numbers. 7 is a prime. I'll go quickly for the rest of the numbers. 9 is not because it's divisible by 3. 11 is a prime. 13 is a prime. 15 is not because 15 is divisible by 3 and 5. 17 is a prime and 19 is a prime. So you can use a similar way to check any number even beyond 20 or beyond 100. So this is just a simple example to show you how to looking for prime number. So the next example, Let's try something larger than 20 or larger than 100. So what if I have a number 113 and I want to know if this is a prime number? So this would be a good example to show from the very basic definition of prime, and then to check whether a given number is a prime or not. And the reason that I'm saying from the very basic definition is that here, this means we need to check all possible factors from this number one by one, and to see if it's really only have two factors, which are number one and the number itself. So do we have other factors other than 1 and 113? So consequently, we need to check them starting from 1, or in fact starting from 2. Right? So is 2 a factor of 113? It is not, because it's an odd number. So now remember, here we can start using the conclusions that we just learned from the previous lesson. We can save a huge amount of time by, instead of writing the full division, we can take the shortcut to tell whether a number is divisible by some certain numbers, right? So first of all, I don't even need to write this. It's an odd number, so it's definitely not divisible by 2. And then how about 3? For 3, remember, I can sum all the digits and to check whether the sum is divisible by 3. So the sum of the 3 digits are 1 plus 1 plus 3 is 5. 5 is not divisible by 3, so 3 is not a factor to that. And how about 4? Now, there's 2 ways. So first of all, you can remember the way to check whether a number is divisible by 4 is to check the last 2 digits and whether it's divisible by 4. And obviously, it is not, but there's another way that we keep seeing that in the past, such that if this number is not divisible by 2 already, then it must not be divisible by any other numbers that contains a factor of 2, right? So this can be even extended to other even numbers such as 6, 8, 10, and keep going, right? This is actually the similar manner that when I eliminating the non-prime numbers, I can eliminate all the even number right away. Here, it is because it's not a multiple of 2, then for any other number that already has a factor of 2, it will definitely not a multiple of this number, right? Because if number A is multiple by 2, it must be able to written as sum n times 2. But if it's also a multiple of 4 or any other even number, then this can be further written as a new integer times 2. Because even number is an integer times 2. So then there must be at least one factor of 2. Then it contradicts to the original conclusion. So which means we can then start from here, skip all the even number. Because it's not divisible by 2, then it will for sure not divisible by all other even numbers. So by skipping all the even numbers, we can check 5. Remember, to check 5, we check the last digit. The last digit is 3. It's neither 0 nor 5, so it's not divisible by 5. and we skip 6, we can check 7. Here, like again, remember the conclusion we had. There's no easy way to check whether a number is divisible by 7. So this one we will have to do the division by ourselves. And then this divided by 7 is 11 minus 7 is 4, 43. This is 42 with remainder of 1. So it's not divisible by 7. And then we skip 8, it goes to 9. Again, remember 9, we need to check the sum of the digits. This is 5, so it's not divisible by 9. So then the whole number is also not divisible by 9. We skip 10, we go to 11. Now we can keep checking 11, 12, 13, 14, but instead here, when you reach 11 and compared to your original question, you find that if I have 11 times 11, I get 121 already. This number is greater than 113. And because I already eliminated all other factors that is less than 11, which means beyond this point, the minimum possible combination will be 11 times 11 if there exists a factor other than 1 and itself, right? In other words, I can still try different numbers beyond this number. For example, I can still try 13, I can try 15, I can try 17, I can try whatever number I like, but the minimum possible combination is 11 times 11, which give you 121, is already greater than your target number 113. So this means that there's no need to further check. Right? No need to check because all other possibilities are not going to reach your target number. So we can stop here and we can claim that this number 113 only have exactly two factors, which is 1 and itself. It has no other factors, so that it is a prime number. And before we finishing this example, one last comment or one conclusion that we can now conclude from this example is that first, when we checking a number, whether a number is a prime number, we in fact don't have to check all the numbers that is less than this number. If you see the examples and see what I derived over here, that means if I already proved a number is not a factor, then the multiple of this number must not be a factor as well. So this means I only need to check all the prime numbers or the prime factors. So basically for this number 113, I can check 2, I check 3, I don't need to check 4. I can check 5, I can check 7. In fact, I'm already checked number 3, so I don't even need to check number 9. So which means I don't need to go through all these numbers one by one. I only need to go through the prime numbers that is smaller than your target number. So this is the first point we can conclude from here, and we can shorten the time. And second conclusion from here, right? Remember why we stopped here, because if we keep going, then the outcome or the minimum outcome, it must be greater than your target number. Then there's no need to keep going. So, which means we can stop at a certain point in time. And where do we stop? here it's coming from the example of 11 square, right? So which means in this example it's square root of 113. So which means only the prime numbers whose square is less than 113 need to be checked. Let me write it down in plain language. So only primes whose squares are less than or equal to the number, the target number, or the number we are testing. So this gives you a stop point that you don't really need, even though you only need to go through all the prime numbers, but you don't need to go through until the number itself. You can stop at the square root of your target number. And from the example we saw, there's another interesting point that you may already notice that is if you have a factor, the factor usually comes in pairs, right? For example, if I have a number 20, well, 20 is an even number, so it's obviously not a prime. But if I'm pretending that I'm checking the primes starting from the first prime number, then I still check it with number 2, right? So if number 2 is a factor, 2, which means number of 20 can be written as 2 times 10, right? So I can check number 3 is not a factor, but number 4 is also a factor. And if number 4 is a factor, that means 20 can be written as 4 times another integer. Here it is 5. And then if I check 6, 6 is not a factor. Sorry, I checked 4, and if I check 5, 5 is also a factor, and actually we just saw it from here. So if 5 is a factor, then 20 can be written as 5 times 4. And then 6, 9, 7, 8, 9, until 10, we find that 10 is also a factor of 20, and that means 20 can be written as 10 times 2. And then if you go beyond 10, first of all, you actually don't even need to check the number beyond the square root of 20. But if you still want to check, you can list all the possible numbers to test, and none of the numbers are divisible by 20 anymore until you reach the number 20 itself. So maybe I can write two more items. It can also written as 1 times 20 or 20 times 1. So you can see that all the factors are coming in pairs. If you have a factor of 4, you must have a factor of 5, and 5 and 4 come in same time. Or you have a factor of 1, you must have a factor of 20. If you have a factor of 2, you must have a factor of 10, right? They're all coming in pairs. But does that true for all numbers? It's actually not. There's one special case, and there's only one special case, is the perfect square. Right? Because as you can see, technically, yes, all the factors are coming in pairs. But what if this number is the same as the other number? Then what happened? For example, 16. Right? I had 2 times 8, 3, nothing. If I have 4, 4 times 4, right? And then I go with 5, 6, 7, 8, 8 times 2. And there's no other factors than 1 and itself, right? So then I can still see that, well, 1 and 16 come in pair, 2 and 8 come in pair, but 4 is not coming in pair because 4 is just 4. It's just one number, 4. So this concludes that only for perfect square, if a number is a perfect square, you will have odd number of factors. And otherwise, if you are not a perfect square, you always have even number of factors. Even if you are a prime number, you will still have one pair of factor, which is 1 and yourself. So this is a very interesting conclusion that good to know and might help you in solving some of the questions. Okay, let's see one more example before we go into the next part. So this example, find all pairs of primes such that their sum is 61. So I need to looking for two numbers. Their sum is 61, and this number themselves are also prime numbers. So we can start by looking at the property of the only known number 61 over here, because we know that it's, well, pair means there's only two numbers. So I have two numbers plus each other, and if I end up with a odd number, that means these two numbers must be one even and one odd. Right? If you don't believe that, you can try different examples. For example, if I have two even numbers, the sum is always even. And if I have two odd numbers, the sum is still always even. Well, here it's only for two numbers. So the only possible sort of combination is only if you have an even number plus an odd number, then you can end up with odd number, right? So which means R and S, these two unknown number, must be one even and one odd. Now if we go back to the definition of primes, or remember the list of prime numbers, we had one observation such that there's only one even number that is prime, which is 2. Right? So 2 is the only even number that is also a prime number. So then, which means these two numbers, there must be a 2, because 2 is the only even prime. And we need at least, well, we need exactly one even number from here to making sure the sum of the two is a odd number. So the one number must be 2. Then how about the other number? If I use 61 minus 2, I get 59. So the other number has no other choice but need to be 59. Then let's check. You can use the way that we just learned, and you can find that 59 is a prime number. So then the solution is that the pair of the prime numbers are 2 and 59. Next, we will take a look at what is prime factorization. In this lesson, we'll just show the definitions and some simple examples, but this will be very useful in the next lesson when we start learning the least common multiples or the greatest common divisor. So over there, you will need to do a lot of calculations to do the prime factorizations. So this will be, even though you will see that the definition is relatively simple, but this will be very helpful in the future. So what is a prime factorization? So we already know that factors or factorizations, again, any number we are able to find its factors in different ways, and the factors could come in pairs or not in pairs for perfect square numbers, but we are able to write factors of a given number. So what is the prime factorization? So this is to write any integers as a product of, like, factors are coming as the products of prime numbers only. Right, so for example, number of 12, there's many factors at a glance, but I can just start writing from some obvious factors. So first of all, it can be written as 2 times 6, and then obviously the number 6 can be further written apart. So 6 is 2 times 3. And then up to here, if I'm trying to keep writing apart, it looks like there's no other factors I can factor out. And in fact, all the remaining numbers such as 2 or 3 are prime numbers, and prime numbers do not have further factors other than 1 or itself. So it looks like I'm going to stop here, and this is the combination or all the factors that I can written for the number of 12, right? So up to here, this example seems a bit random. Is there a way that to help us making sure that we're writing out all the prime factors, where we're not left out anything, right? So there's a certain format called factor tree. This is like the first time you learn long division or long multiplication, so this can help you looking for the prime factors step by step. So for example, I'm still using number 12 as example, so I can start with the smaller prime first to the bigger prime, so which means I can start with 2. Number 2 obviously a factor of 12. And if it is already a prime number, which means this do not have further breakdown, so I can circle it, which means it will stop here. But on the other side, 12 is 2 times 6, and I'm not circling 6 because 6 is not a prime number, which means it can be further breaking down. So 6 is in fact 2 times 3, and both 2 and 3 are prime numbers, and there's no further breakdown for them, so I can stop here. So 12, and then I will only write the numbers that I have circled because those are the terminal numbers, so those are the numbers by the end. So it's 2 times 2 times 3, so this will be the same as how we derived over here. And further, we have already learned exponents, so this can be further written in a bit more compact form, that is to group the same number as exponent. So it's 2 squared times 3 to the power of 1. So I'm not going to write 1 here. Right, so let's see another a bit more complicated example. Let's have a 3-digit number, 252. We always start from number 2, or in other words, we'll always check whether this is a even number or odd number. And if this is even number, or if the breakdown is still an even number, we can keep trying to until reduce this number to an odd number first, right? So this can kind of save some energy by not thinking too complicated, but just keep trying number 2 even number. So this divided by 2 is 1, 2, 6, right? So again, it's a even number, so I don't even need to bother anything else. I'm just keep dividing this by 2. I will get 6, 3. Okay, now it's no more factor of 2 because it's an odd number. Then we move to check number 3. Again, remember the shortcut we learned that we can check by adding the 2 digits together. 6 plus 3 is 9. 9 is divisible by 3. So this number is very likely, or this number should be divisible by 3. So if I divide by 3, the left or the remaining is 21. 21 is again can be divisible by 3, and it's actually 3 times 7 equal to 21. Now this 7 is a prime number if you still remember that, or even if you don't remember that, you can try see number 2 not divisible, 3 not divisible, 4, 5, 6 are all not divisible for this number 7, right? Or you know this right away that 7 is a prime number, so which means there's no further breakdown to up to here. So then I can write them together. Again, I don't bother with the number in the middle. I only care about the number by the end. So it's 2 times 2 times 3 times this 3 and times this 7. And then I can further write it in a compact form of 2 squared, 3 squared, and 7. Right, so this is how we find how we use the factor tree to find the prime factorization. Now, fundamental theory of arithmetic. So this tells that every positive integer has a unique prime factorization. Okay, unique prime factorization. So which means this and this is a unique combination. So you may ask, like for example, here I divide by 2 first. What happens if I divide by 3, right? What happens if I divide by 7 over here? Do I still get the same results? We can quickly try this. Now start from here. If I choose to divide by 7, that is fine. So then this divided by 7 is 1, 12 minus 7 is 5, 56 is 8, right? And then I can divide by, let's say, 3, because 1 plus 8 is 9. It's divisible by 3. So then it gives you 6. Well, 6 is 2 and 3. There's no other combination. So then this can be written as 2 times 7 times 3 times 2 times another 3. And if I'm going to just reorder this number or to simplify this in a compact form, I will still get, I have two 2's, so it's 2 squared. I have two 3's, get 3 squared. I have 1 7. So after all, it is the same, right? So this means doesn't matter which number or which prime number you are factoring out first, eventually you will always get to the same prime factorization. So here you can consider the prime numbers as they are the basic element of numbers, and because they are basic elements that they cannot be further factored out, so then this prime factorization is a unique combination for every single number. Let's just see one more example to find prime factorization of 36. So this time I'm not going to, you can still feel free to use the factor tree by yourself, but here to fast forward a little bit, I'm not going to use the factor tree, but I'm still use the same way. Actually, I can use the random factor to start with. This will, based on the fundamental theorem of arithmetic, this will end up with the same combination of prime factorization. So here in the number 36, it's obviously a perfect square of 6, so it's 6 squared. And then number of 6 can be written as 2 times 3, the square. So then remember what we learned in exponent. So it's 2 squared times 3 squared. Right, if you want to factor out 3 first, because this number obviously has a factor of 3, then in your 12 is 3 by 4, and your 4 is 2 by 2. Eventually, it's still 2 square and 3 square, right? I can write as many different combinations as I want, but eventually the result's always the same, because this is only have one unique prime factorization. Similarly to another example, 144 is also a perfect square. It's a square of 12. Then 12 is 3 times 4, but it's further 2 times 3 times 2. Maybe I should write the prime factorization of 12 first, which is 2 squared times 3. And then our original question, it's a perfect square of 12. So we have a square here. Again, this is what we learned in exponent. So this can be simplified by, so this is square power over power, power of power. So then this is 4 and 3 squared. Okay, so this is a one simple example. Okay, maybe let's see one last example to conclude this lesson. So we let a number n to be the product of the first 10 prime numbers. So then this n can be written as 2 times 3 times 5 times 7, 11, 13. You can look up the prime numbers in any reference from any reference page or from any websites. There are list of prime numbers that people are listing. So here I'm really just copy down the first 10 primes, right? So up to here, if n is a number such that it's a product of all these numbers, then obviously n has many factors such as 3 or 11 or 17, right? Any number here, because it's a product, so it is also a factor of n, right? This is pretty clear and no ambiguity. So, but then the prime factorization of a new number n plus 1, this number must include a factor that isn't among the 10 smallest primes. Okay, to simplify this question or to explain this again, we first construct a number n that is the product of the first 10 primes, so which is here. And because it's a product of 10 primes, which means each one of this number here is a factor of n. This is clear, right? Because it's n is the product of these numbers. But here the question is about n plus 1. So we claim that from n plus 1, there is no factor, or even if there's existing a factor, that factor is not any of these 10 numbers. 29 plus 1. We can try a couple examples before we prove that. For example, we claim that this number n plus 1 doesn't have factors such as 2, 3, 5 to 29. So let me pick a random one to check. Let's check 13, for example. So n divided by 13 is definitely an integer. It's actually 2 times 3 times only except 13, but the product of all other numbers, which is obviously still an integer. So n is divisible by 13 for sure. But how about n plus 1? N plus 1 is 2 times 3 times 5, 29 plus 1. And if I want to divide by 13, this means I can at least have a multiplier here that is 2, 3 till 11. And then we jump over 13. We have 17, 19 till 29. If I take this number, multiply by 13, it will equal to this original number of n. And then I take the difference of these two numbers. This is just plus 1 of the original number, so the difference must be 1. So then I have a remainder of 1, and then this remainder 1 is smaller than any other factors over here, which means it is not divisible such that you have a remainder that cannot be eliminated. So first of all, we show that it's not divisible by any of the existing factors 2, 3, 5 until 29, right? So which means if there is a factor to this n plus 1, it's guaranteed not among this list of number. And this list of number already contains all the prime numbers, or this already contains all primes from the first 10. So which means next eligible prime must be greater than these numbers. Right, so then I'm not saying that you may prove this n plus 1 is prime or not. It doesn't important, because as long as I know the factor of this number must be greater than 29 or must be greater than all these numbers, then you either have a factor greater than 29 but it's prime, or the factor can also be n plus 1 itself, because n plus 1 could be just a prime number itself. Then the factor can only be n plus 1 itself, and n plus 1 is also a number that is obviously greater than all these numbers, right? So this proves that the new number n plus 1 must include a factor that isn't among these given primes. So how do we, why we have this example, and how or why we are interested in proving this? This gives you a further conclusion, that because people may want to ask, is there infinite many of primes? Or if I find a prime number, do I guarantee to find another prime number that greater than this one? Right? Because looks like as you keep going on, or as the number becomes larger and larger, it seems easier to find more factors from that number. So this actually proves that I can always construct a new prime number, or a new number that is greater than any known primes. Like, for example, assume that I'm at a very early stage of learning mathematics. I'm only able to find 10 prime numbers so far. So I don't even need to bother to find the next number, but I can claim that if I construct a new number n plus 1 to be the product of all the known primes, it don't have to be 10, it can be 100 or 1000. If I find 1000 primes so far, I can always construct a number to take the multiplication of all these known prime n plus 1. So this concludes that there are infinite many primes, or in other words, there's always be a prime number that can be found greater than the current known prime number. So there is no largest prime, because there are infinite many primes, and I can always find a prime that is larger than that.